the pigeonhole principle 1. The pigeonhole principle comes from our observations on pigeonholes. Let's look at this example. Say, if 11 pigeons fly into 3 pigeonholes, then some pigeonhole must have at least 4 pigeons. And let's think about this one. So if you think 11 pigeons go into 3 pigeonholes, then divide by 3. On average, each pigeonhole must have at least 3, which means one pigeon need to go to one hole with 3 pigeons, so it means at least there will be 4. But here is the proof. So let's consider by contradiction. So by contradiction, now this is the case if P, then Q. So if we use contradiction, then we need to negate Q. So the Q here is some pigeonhole must have at least 4 pigeons. To negate that means for some, negation is every. And then must have at least 4, at least means not more than. So negation of at least will be not more than, will be less than 4. So therefore, we negate that, it will become, so by contradiction, we will say, assume every pigeonhole has no more than 3 pigeons. Because if it has 4 pigeons, then it satisfies this one. So when we negate this one, then it has no more than 3, that including 3. So if each pigeonhole has no more than 3, then the maximum is 3. Then all 3 pigeonholes together have 3 times 3, because you have 3 pigeons and 3 holes, so total is 9. But this is a contradiction. This contradicts to 11 pigeons. So therefore, the contradiction means some pigeonhole must have at least 4 pigeons. Therefore, some pigeonhole must have at least 4 pigeons. From this example, we can summarize the example to get a statement of the pigeonhole principle. The pigeonhole principle. If a finite set S is partitioned into K subsets, then at least one of subsets have cardinality of S divided by K or more elements. Remember, this is the notation of cardinality, and that stands for the number of elements in S. So in our example just now, the S is 11 pigeons. So the cardinality of S is 11. And then we have 3 pigeonholes, and that is 3 subsets. Therefore, there will be cardinality of S divided by K. That will be 11 divided by 3, but this is 3.66. So, and then that gives us 4 pigeons. To prove the pigeonhole principle, the idea is the same as the example we just discussed. That A sub 1, A sub 2, A sub 3, and A sub K be K subsets. So K subsets is like a K pigeonholes, because then each pigeonhole hosts some pigeons. And then by contradiction, assume no subset has cardinality of S divided by K or more elements. So that means the cardinality of A sub 1 is less than cardinality of S divided by K, and made a mistake, made an error here. So this instead of S should be K. And then similarly, A sub 2, the cardinality should be less than cardinality of S divided by K, because by contradiction, we assume no subset. Okay, again, we need to negate this one. At least one subset has this much. So negate, this means at least, for at least when we negate, that means everyone. And then the subset has this one or more, then that means the negation will be less. So that's why we have this. And then A sub 3 is less than cardinality of S divided by K, and for every A sub K. So that will be the last one here, and that is less than this. So if you add all these cardinalities together, A sub 1 plus A sub 2 plus A sub 3 plus A sub K. So that's the left-hand side of these inequalities. That should be less than, you add all the right-hand side together, and that is cardinality S divided by K, and you have K, so multiply by K, you can cancel the K, then you get cardinality S. So this altogether is cardinality of S, because you have K subsets. So then they are disjoint, then the cardinality will be the sum of them. So that will be this. And then it's less than this one, and this is a contradiction, right? So the contradiction proves the, here is a simpler pigeonhole principle statement. And this one you can see from the book. The simpler statement is that if more than n objects are to be placed into n categories, then some category must receive more than one object. So, and then this one is like the example we did. There are n objects, so like 11 pigeons are to be placed into n categories, and like we just now we have is 3 pigeonholes. Then some category must receive more than one. So, and then here is n to n, then some will receive more than one. But just now when we talk about 11 and 3, then the average 11 divided by 3, and it's 3.6, so the nearest closest is 4 pigeons. Okay, so this is a simpler statement. The pigeonhole principle is also known as the drawer principle. For example, 11 pigeons are like 11 socks, and 3 pigeonholes are like 3 drawers. So if you put 11 socks into 3 drawers, then each drawer, some drawer, you need to put at least 4 socks. Let's look at another example, and this example is in the book. X stock drawer contains 7 blue socks and 12 black socks, unfolded and unsorted. On a dark morning, Ed blindly reaches in and draws socks from the drawer. How many socks must Ed take to be guaranteed of getting A, 2 socks of the same color, B, 2 black socks, and C, 2 blue socks? Here we have 2 different colors, blue and black. So therefore, it's like 2 pigeonholes. one is blue, another one is black. So if we want to get, the same color, then you need to think about like 3 pigeons flying into 2 holes. Then one pigeonhole will have 2 pigeons. So now we may apply the pigeonhole principle. So by the pigeonhole principle, and we say there are 2 categories. So one is black, another one is blue. And then if we have used 3 socks, then each sock will go into one category. So then you have third one, and that third one will belong either the black or blue then. So therefore we use 3 socks. Then by the pigeonhole principle, we place 3 socks into 2 categories. Then one category has at least 2 socks. Thus, 3 socks drawn blindly can ensure 2 of the same color. To answer question B, actually we use a technique called the worst case analysis. So we use the worst case analysis. This actually we do not use the pigeonhole principle. Now, the worst case analysis, if we want to get 2 black socks, the worst case is we get all the 7 blue socks first. So we get all 7 blue socks first. Then the last 2 must be black. Therefore, altogether we need to have 2 plus 7, so we need 9. So we need 9 socks to guarantee 2 black socks. For question C, similarly, we still use the worst case analysis. So this time, to get 2 blue socks, the worst case is we get all the 12 black socks first. So the worst case, we first get all 12 black socks. Then the next 2 must be blue because all the black socks has been taken, then the next 2 must be blue. Therefore, we need 14 socks to ensure 2 blue socks. So to answer question A, we use pigeonhole principle. And then for the other 2 questions, we use the worst case analysis. The worst case analysis is often used for examples like this. We would like to explain one more example, but that is a long example, so we will stop here and then we will create another lecture to explain the next example. Then we will give you homework assignment. Thank you.